Okay, dear students, now comes question number 19. It's about integrating factor. So before we calculate the integrating factor, let's talk about what integrating factor is. As students, as we discussed up to now, whenever in a given differential equation, the coefficient, treating coefficient of dx as m and coefficient of dy as n, once it is written as m dx plus n dy equals 0 form, if the partial derivative of a with respect to y comes to be the same as partial derivative of n with respect to x, we said that the given differential equation is exact. But you need to know that not all differential equations are exact. There are a lot of non-exact differential equations. But what you need to know is certain non-exact differential equations can be changed to exact differential equations by applying or multiplying the given differential equations by a certain expressions of x and y. So this multiplier or this function that can change the given non-exact differential equation to exact differential equation are called integrating factors. So integrating factors are simply multipliers or factors that enable us to change non-exact differential equations to exact differential equations. Now I'm going to show you the two kinds of integrating factors here, okay? Integrating factor depending on x alone and integrating factor depending on y2, okay? Now let's see how we can find integrating factors for some sort of differential equations. So here I begin. It says find the integrating factor for this particular differential equation. So the solution for this runs as you see. Look students, this can be rewritten in terms of this one. As you see, x into 1 minus xy y prime is equal to y plus 2x squared can be written like this. Look, you're having here dy over dx, guys. So when you multiply the whole by dx, y plus 2x squared will have a dx, you see, as you see, and this will have, look, dy. You can multiply x by 1 and you can get here x minus x squared y. But as you are taking this expression to the right, this will have, you see, a negative of this expression and this will result. So dear students, now you can consider this one as your m value. You can also consider this one as your n value because the coefficient of dx is m here and the coefficient of dy here is n. So let's now check whether my and nx are the same or not. You see, where my is a partial derivative of m with respect to y and here nx is a partial derivative of n with respect to x. So from this, as you see, m is y plus 2x squared, so the partial derivative of m with respect to y is 1. Because this is an expression of x, it will have, you see, 0 value when you look for its partial derivative with respect to y. So this is, you see, what you can have. Let's proceed to n. N, according to the way it is written, n is x squared y minus x, guys. So the partial derivative of n with respect to x now comes to be 2xy here minus 1, right? 2xy minus 1. Now look, if you compare my and nx, they are completely different. So this shows you that this differential equation is not what? Exact. This or this one. Both are, you see, equivalent, the same. So this equation star is not what, students? Is not an exact differential equation. It's non-exact because my and nx are not identical. Now, the question is, how can we change this non-exact differential equation to exact form? To do that, we need to now calculate a certain multiplier, okay? A certain multiplier or a function that can change, you see, the non-exact one to the exact one. And this multiplier is called integrating factor. So let's find now that integrating factor, the one that enables us to change the non-exact one to the exact one, okay? So for that, let's calculate my minus nx, the difference of the two. So the difference of the two cannot be 0 because, as we said, you see, this is not what? Exact. So my minus nx is going to be, look, my is 1 already obtained minus your nx is 2xy minus 1. So as you are taking the difference between the two, you will obtain that to be minus 2xy plus 2. Negative makes 1, 1 plus 1 makes 2, minus 2xy plus 2 can come. So this basically is, you see, different from 0. You see, students, this is different from 0. Had it been 0, this would have been, you see, exact. But for the time, it's different from 0, so it is non-exact differential equation. So now how can we change this non-exact to exact? Let's find this integrating factor. So this, now let's proceed into the next one. We are having this one. Look, students, my minus nx is already determined. It's obtained to be this one, minus 2 into xy minus 1. Now let's divide this difference by either m or n. What matters is the case where you can have a single variable, you see, as an output. Suppose if I divide this by m, what's going to happen? Let you see. If I divide this expression, my minus nx, this expression by m, here is m. Copy this and paste here. You see, nothing can be simplified here. So you are going to have expression of x and y's at the same time. So you don't need to divide this by what, students? By m. Now let's divide this by n and see what's going to happen. Your n here is this one, so copy and paste here. Look, x squared y minus x. Now thanks to certain simplification, mathematical simplification, one can easily obtain this minus 2 over x. Look, this is minus 2 into xy minus 1. As you take x as a common out here, x into xy minus 1 is going to come. Now we can simplify one over the other, you see, then minus 2 over x can come. What have you obtained? Finally, you obtain this to be a function of x. If you obtain this to be a function of x, the integrating factor can easily be obtained. The integrating factor can be obtained by making this to be g of x because it's a function of x. Now the integrating factor is nothing but it is obtained by using this one. The integrating factor I of x, when I use I mean is the integrating factor. So this is a power of the integral of g of x dx. You use this if and only if this difference ratio, you see, is obtained to be a function of x. You see, a function of x. What if this is a function of y? If this is a function of y, if when it is divided by m, you need to use minus of, you see, an expression of y here. You may call it h of y. Now, for the time being, this is a power of integral of g of x dx. So this has to be used. And this is equivalent to e into, we knew what g of x is. It is minus 2 over x dx. So this is e, the power of the integral of negative 2 over x dx is minus 2 ln x, as you know. And this is e the power of ln of x, the power of minus 2. We can take this minus 2 up, no problem, using Lagrange's property. So this is going to be x the power of minus 2, as can be shown. And this is equivalent to 1 over x squared, as can be shown. This is 1 over x squared. So the integrating factor is 1 over x squared. What do you mean by saying that? This means if you multiple, this is an exact one, the one written here, you see, by 1 over x squared, this is no longer non-exact. It will automatically change to exact one. Okay, students, let's you check that, please. Look, when we multiple the equation star by 1 over x squared, what we can get is this one. Look, 1 over x squared times the entire equation star is directly taken. What comes here is, as you see, this one, y over x squared plus 2 dx plus y minus 1 over x dx, which actually is exact because the partial derivative of this one with respect to y is, you see, 1 over x squared, as you see, and the partial derivative of this with respect to x is 1 over x squared again. So this is an exact one. So thanks to this integration, this integrating factor, the non-exact one is changed to the exact form. Similarly, students, let you take this again. You are asked to find the integrating factor for this expression. So as usual, what you need to do is you have to identify m and n. So clearly, m is a coefficient of what? Dx. Don't consider m to be this one because this is n, because it's a coefficient of dy. So you have to consider this one as your m, which actually is 4xy plus 2y squared. And the coefficient of n dy is considered to be your n, so that is 2xy plus 5y is the power of 4. Now we need to calculate my and nx. So as you see, my and nx are obtained, as can be shown. Partial derivative of m with respect to y makes 4x plus 4y for m, partial derivative of n with respect to x makes 2y. So now let's take the difference between the two. As can be shown, the difference between the two is 4x plus 2y. You see, because when you subtract this one 2y from this, 4x comes as it is, but 4y minus 2y is 2y, which actually is different from 0. So this is non-exact, students. So we need to calculate now the integrating factor, the one that enables us to change the non-exact to exact. So let's calculate now. My minus nx is taken. You see, it is obtained to be 4x plus 2y. Now let's see what's going to happen if I divide this by n. n need this, students, n need this one. You see, students, so if I divide this by n, this will never be a function of single variable, okay? So I have to reject that. Now let me divide this by m. M is this, students, y into 4x plus 2y. Y into 4x plus 2y. Look, 4x plus 2y can be cancelled by 4x plus 2y, so 1 over y can come. So clearly, the integrating factor now can be obtained by letting h of y to be 1 over y. Previously, it was a function of x, something different. But in the case of, you see, a function of y is obtained, our integrating factor is going to be obtained by using this one. E is a power of what? Minus of the integral of hy dy. You have to be careful, dear students. In the case of integrating factor which is given in terms of x, you were using simply e is a power of the integral of g of x dx. You were not having this negative sign. So whenever you divide by m, you have to be careful. It will be a function if it is given in terms of y. Don't forget to use minus in front. Otherwise, you can interchange these two and have positive value if you want. So this is the idea. So this is e is a power of minus of the integral of 1 over y dy, and this is equivalent to e is a power of minus ln y. You see, I just took h of y to be 1 over y directly here. And this minus is gonna go up, and y is a power of minus 1, which actually is 1 over y, can be the integrating factor. So it is this 1 over y that enable us to have this non-exact one to what exact form. So let's see how that can be done. So let's multiply the given equation by 1 over y and see what's going to happen. Look, when you multiply this 1 over y, the original differential equation, the question we are having in question 20, by 1 over y, look, no more y, so 2x plus 5y cubed can come, and there also no more y here, 4x plus 2y can come. So if you perform the partial derivative of the coefficient of dx, which is this one, with respect to what? Y, my, it will be what, students? It will be 2, as you see. And the partial derivative of this one, the first one, which is the coefficient of dy, which is treated as n, with respect to x, again 2 can be obtained. So this shows you that the given differential equation has been changed to, see, exact form thanks to what? The integrating factor.